Hey guys, 9.8. Whoa! Getting long, okay? 9.8, that's okay. This is a pretty good one. Aldehydes and Ketones. Can't get a more exciting title than that. I don't remember if you remember what aldehydes and ketones were, but let's take a look here and see what we got. An aldehyde, remember, is a carbonyl group, and it's at the beginning or the end of a molecule, so it only has a hydrogen here. So remember, a hydrogen can only have one bond, so there's nothing any further to the right or to the left of that. It can have anything over here on this side, but that carbonyl group has to be at the end or beginning of a molecule. A ketone, on the other hand, is the same carbonyl group, but it's in between two carbons so that the chain can keep going further that way or it can keep going further that way, but it's in the middle. So it's something to keep in mind, all right? Nothing crazy. Here's some common aldehydes right here. Formaldehyde, this is, you've heard of that before, just this little simpler one right here. It's used, what I always remember is what we used to embalm our cadavers with. Oh, not me. I've said too much already. I meant when I was in college and stuff like that, we had to deal with specimens and things like that. That's what they used to do them in. I think now they do them in something called formalin or something. But they also have vanillin, of course, for vanilla. And cinnamaldehyde is another one here that makes things taste like cinnamon. So those are the common aldehydes. Common ketones. Acetone, that's your nail polish remover. That's the most common one that you guys would know. Muscone, you might have heard some people out there say, I'm going to put on some musk or something like that. That is basically in perfumes or in cologne and stuff like that. But that's isolated from musk deer, so it's kind of weird. And then you have beta ionone, which is also, it's found in lilacs, I think, or no, violets. Violets is right. And it's used in perfumes as well. So these things generally smell a decent amount. So they either smell bad, like nail polish remover, or they smell good, like that. All right, keep it rolling here. Shortcuts for writing aldehydes and ketones. If we look here, we got a CH3, a CH2, a CH2, but then let's just, at the end, we put a CHO. That's what that's all about. So if you see a CHO at the end of a condensed molecule, that means there's an aldehyde there. There's another one right there. What about a ketone? Where do we write those? You'll see a CO in the middle of it right there. So that CO means that carbonyl group somewhere in the middle. And that's what we're looking at. So that's something to keep in mind of how it works. I don't know, let me know if you have any questions on that, but you'll see them here in a little bit. Let's see, naming aldehydes, they end in AL, kind of like alcohols ended in OL. These are going to end in AL, so it can be a little tricky. You got to pay attention. It's only off by one letter. So this is based off of one carbon, which is meth, which is why we call that methanal, right there, methanal. You don't hear that very often. And then this one's based off of two carbons. See how it's an aldehyde here? See it right there? And that's called ethanol right there. So that's how it works. It's essentially just like ethanol or methanol, but it's al because it's an aldehyde. All right. Naming ketones right here. We generally will name the ketone based off of where the carbonyl group comes off of. You can see that this carbonyl group is coming off of carbon number 2 right there. So we would call that 2-pentanone. Notice that it ends in one there. So this would actually be called 1, 2, 3, 4, 5 pentane. But since it has that, it's pentanone. All right. This guy right here, this is also pentane, or it's based off pentane, but the carbonyl group's coming off of number 3. So it's called 3-pentanone. That's how we look at that. So something to keep in mind when you name these things. Let's look at their physical properties here real quick. I'll have to move my, I think I'll have to disappear for a second. I'll be right back. All right. So let's see. We've got CH3. Look at these guys. These have the exact same molecular weight, but this was an aldehyde. Now, let me go back. Hold on. Okay, look at these aldehydes and ketones. Okay, so here's an aldehyde. Notice this hydrogen is not directly connected to an oxygen, a nitrogen, or fluorine. So this is not hydrogen bonding in aldehydes at all. It is polar because it has an O up here and no O's down here. So these are polar molecules or dipoles, all right? Same thing with the ketones. There's no hydrogen bonding whatsoever, but you do have a polar molecule. So this is also a dipole. So the only intermolecular forces that we have are called dipole-dipoles. So here we go. Look, this guy right here, let's look, same exact molecular weight. This is an alkane, so it only has London dispersion forces. This is the aldehyde. It has dipole-dipoles. So look at the difference in their boiling points, and look at the difference in their solubility. A polar molecule can be dissolved in water. A nonpolar cannot, all right? Keep it rolling. Look at these two. Here's a ketone. Here's a hydrocarbon. Same exact molecular weight, right there. But look at the difference in the boiling point, because ketones are also dipoles. So we have dipole-dipole action here, and only dispersion forces here. But once again, polar molecule, soluble, and not soluble for the alkene. Same thing happens here. Look at this. Boom, 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 boom. Hydrocarbon, it's nothing more than a nonpolar thing. Low boiling point. This is an aldehyde and a ketone, and they have much higher boiling points. And also, they are soluble here, and the nonpolar one is insoluble. All right. So there you go. All right. I'm back. Okay. So let's look here. So here's what you got to. This is a quick summary. Hydrocarbons only have dispersion forces. They're going to have a low boiling point. All right. Alcohols had hydrogen bonding. They're going to have a high boiling point. All right. Aldehydes and ketones are right in the middle. Okay. They're in between the hydrocarbons and the alcohols. As far as solubility, remember water is a polar molecule, which means like dissolves like. Hydrocarbons will not dissolve in water because they're nonpolar, but aldehydes, ketones, and alcohols will be soluble in water. The way they get more soluble is if they get a lower molecular weight or lower molar mass, okay? Let's look. Let's check it out. So let's say we had this situation where all of these, if you look at the ending, they're all aldehydes, okay? But look, they're getting bigger and bigger and bigger. The number of carbon atoms is getting bigger, so these are getting bigger. So their boiling point, of course, goes up because as they get larger, the dispersion forces get larger, which means that we're going to have a higher boiling point. It's going to stick together better. But as they get larger, they also become less soluble in water. So that's something else to keep in mind, all right? So the bigger they get, the higher the boiling point, the stronger the forces to hold them together, and the bigger they get, also the less soluble they get in water. It's hard to dissolve big things in water, okay? Same thing with ketones. Look, there's our CO in the middle. That's how you know it's a ketone right there. But these are getting bigger and bigger and bigger, so guess what's going to happen to the boiling point? It's going to get bigger and bigger and bigger because the dispersion forces are getting higher and stronger and everything. But as they get larger, they become less and less soluble in water. So they're still slightly soluble, even down there with 6 carbons, which is pretty impressive, okay? Let's see. Here is the one slide. I'm going to move my picture over here if you don't mind. There we go. This is the one slide of dealing with the reduction of these things, or the chemical reactions of them. So here is the reduction of aldehydes. This is exactly the opposite of what we saw when we were dealing with alcohols. Okay, so the alcohols went one way, the alcohols were here, and they went that way. We've already talked about them. Now we're doing the opposite of them. So if we reduce something, remember when we reduce it means we're going to either take away hydrogens, take away oxygens, or add hydrogens, okay? So we're going to add hydrogens to this thing right here. And what's going to happen is one of the hydrogens is going to go with this oxygen. It's going to break that double bond, and then that leaves another bond for carbon to form with this hydrogen here. So what you end up getting is, look at this, you get an alcohol, but that carbon here is only attracted to one other carbon or something. Remember that R just means a chain of carbon somewhere going that way. So one other carbon, that's a primary alcohol, okay? So aldehydes, when they get reduced, form a primary alcohol, if you will, all right? Look at this guy, a ketone, okay? What do you think they're going to form? It's going to be a secondary alcohol, all right? So what we do here, we take the hydrogens, it's going to do the same thing, boom, hydrogen with this one, hydrogen with that one, you end up getting that. But look, that carbon's connected to 2 carbons, so that's a secondary alcohol. Nothing crazy. This is what happened before with alkenes. We take a hydrogen, boom, it just made it into an alkane. So reduction means to add hydrogens or take away oxygens. So we're adding hydrogen in this situation, okay? I think that's it. Hey, that was 9.8. So there's only 9.9 and 9.10 to go. 9.9 clearly is a means. Hope you had a good day today. Take good notes on this and do well on the test, okay? If you need anything else from me, let me know, all right? See you guys.